Hello, my name is Tuck Long, and this is my submission for Project 7. Today I'm going to be presenting a paper by Tobias Batik, Hugo Brumet, Kristina Vasilievska, and Hannes Kaufmann. So this is their paper, Shiftly, a novel origami shifting haptic device for virtual reality. So virtual reality allows us to see, hear, and interact with in virtual environments that I'd say are getting closer to reality every day. But for true immersion, we're going to need more than just sight and hearing. We are going to need to introduce a sense of touch. So previously, building a reliable haptic device has been difficult. Previous approaches have faced massive limitations. You could use simple vibrations, or it could use a pin display, but that is heavy, expensive, and sometimes geometrically limited. So that leads us to our main research question. How do we build a single lightweight device that can simulate the full range of human touch? So this is going to require a fundamental shift in design, and we need a way to change shape drastically while keeping a mechanism simple, light, and low power. And this is what the solution for that comes in, Shiftly. So Shiftly is a shape-shifting haptic device built upon the principles of origami, which is an old art form that transformed paper into complex shapes using creases. This concept was taken and adapted for precise and electrical mechanical movement by Shiftly. And the key breakthrough with Shiftly is that it integrates curved traces, which allows for the origami module to fold and unfold reliably. And that's going to let it transition from a flat plane into a continuous curve. So the prototype they use has 3 individual origami modules on a frame. Each module is controlled by a single stepper motor, and that's going to allow them to fold and unfold independently. What this means is that there's only 3 actuators to manage what would usually require many more, and that's going to keep the device lightweight and easily mountable. The researchers made a kinematic module that allows them to control the physical properties. So say they need a surface with a radius of 46 millimeters, or they need a sharp inner corner. The model is going to interpret that request, and that's going to send it to the prototype for precise motor rotations. To validate their design, they conducted 2 user studies. In the first one, they tested how distinguishable the shapes were. They asked the users to identify the shapes based only on touch. In the second one, they integrated it into a VR environment for their conference attendees. So in the first experiment, the results here show that the haptic feedback was highly distinguishable. In the lab setting, the users were able to group shapes by their category of flat, edge, or curves with high statistical accuracy. In the second experiment, they conducted a real-world test with the special interest group on computer graphics and interactive techniques, and then the users there touched visible objects in VR. As you can see, the cylinder and the wave shapes had high scores, but the rotated diamond was significantly lower, showing where Shiftly's limitations lie. And here are the surfaces that were modeled. So for the first time with using Shiftly, haptics can offer a more plausible experiments, even though the perfect geometric simulation isn't exactly achieved. The findings that the researchers found that suggest that in real-world scenarios, like interacting with complex objects in VR, the sense of touch is influenced by visual feedback. For future applications, I think that Shiftly's modularity makes it appropriate for future applications like surgery or remote workers. It could also be applied to other industries like medicine or design, or involving those industries. So in summary, Shiftly represents a new class of haptics that is low cost, high fidelity, and versatile, and it also makes haptics in virtual reality more accessible.